Big techie guy. Hi, everybody out there in podcast land. This is Mr. Folly, and welcome to AP Podcast 15.1, Intro to Buffer Systems. I think of buffers as being enemies. So, really, what a buffer is it's something that resists pH change. And I didn't put that anywhere else, and I should have. And buffers are enemies. So they're usually conjugates of each other. So conjugates, if you recall, would be like HF and F. So the only difference is whether there's an extra H there or not. So if you buffer an acid, you also buffer a base. So you're a buffer both ways, or you're not a buffer at all. We're going to give an example system of HF and KF. We're going to learn the Henderson-Hasselbalch equation. Yeah, there's a dash. And what happens if acid equals base in a buffer using Henderson-Hasselbalch. And we're going to talk about disturbing an equilibrium system, and that's a titration. And identify the species present pre-equilibrium, at equilibrium, and post-equilibrium. Equivalence, not equilibrium, but you get the idea. So let's hop into it. Bronsted-Lowry acid-base conjugates. So looking at this guy right here, we've got HF and F negative. So there's your conjugates. This is my acid. This is the conjugate base. Buffers resist pH change. If I have appreciable amounts of both of those guys, and here, then, so I need both of the enemies, then it will act as a buffer. So I have to have significant amounts. What are significant amounts? They've got to be significant to each other, so they're going to be somewhere, they're going to be within 100 times of each other. Okay, so for example, if I had 0.01 moles and 1 mole, those would be within 100 times of each other. But if I had 0.01 moles and I'm comparing it to 1,000 moles, that would not be a buffer system because they're not within 2 powers of 10 of each other. And that's my rule of thumb, just so you know. And oops, this is a typo. HNO2 plus H2O yields H3O positive plus NO2 negative. Notice I have, oops, that didn't change the highlighter like I wanted it to. Notice I have enemies, HNO2 and NO2 negative. Probably highlighting yellow with yellow was a bad choice, but we'll deal with it. I have some of each. If I add H positive to the reaction, that H positive will want to react with something. Its favorite thing to react with would be NO2 negative. Positives like the negatives. So H positive plus NO2 negative gives you HNO2. So if I have an OH negative in a reaction, OH negative is going to be attracted to a positive thing, or it's going to be attracted to this acid. So OH negative plus HNO2 will give you H2O plus NO2 negative. Now, what affects the pH in these things? Would HNO2 affect the pH? No. Would H2O affect the pH? No. Would NO2 negative affect the pH? No. What affects pH? Only H positive and OH negative. Anything else? No. Only H positive and OH negative. Now, the other things can be kind of the parent things that go through it, but if you don't have H positives or OH negatives as your product, you are not affecting the pH. So looking at question number 8 from your sheet, buffers don't have to be conjugates, but they probably will be. To show you what I mean by this is I could have a buffer system that's HCN and F negative. This is a weak acid, and this is a conjugate base. And it's a weak base. Really, all you need is a weak acid and a weak base. But they probably will be. A typical way to make a buffer is to titrate a weak acid or a weak base. So looking at letter A, I have Na, 2CO3, and HCl. So when H reacts with carbonate, I'm going to get HCO3 negative, which would be an acid-base buffer system. So carbonate and hydrogen carbonate are conjugates of each other, so that would be a buffer. And a HCO3 and a HCl, and a strong acid, that's going to go away. So the H positive is going to react with HCO3 and give you H2CO3. So now I have another buffer system. Do you see how letter C is like A and letter D is like B? So you're making buffers, you're making weaks and their conjugates and all those other things. So letter E must be the one that's not a buffer solution. Let's look at why. Na has no impact on pH. So CO3 negative 2 is a base, and Na no impact. OH negative is also a base, so a base and a base will not make a buffer. So this is the one that is not a buffer. Good. HF and KF system. Does K matter? No. All you're looking at is HF and KF. So what I wanted to do here was, of course, write things better. HF plus OH negative would give me H2O plus F negative. Again, not making anything that changes pH. And then F negative is very good at addressing H positive. F negative plus H positive would make HF, which again doesn't affect pH. What changes the pH? H positive and OH negative. Is any of that made? No. So what's the change on pH? None, which really is very little. The Henderson-Hasselbalch system. Finding the pH of buffers. Buffers work best where pH is close to pKa. And really what this means is you're going to have appreciable amounts of both acids and base. Use the Henderson-Hasselbalch equation. There's a dash between there. pH equals pKa plus log base over acid. So these would be my weak base and weak acid that go with it. And this is on your equation sheet, and you use it a ton. You should be able to also figure out that POH equals pKb plus log acid over base. So again, we change our acid things to base things, and that would invert the log part. Let's look at some examples of this. No, I'm sorry. What happens if A equals B? If pH equals pKa plus log base over acid, that means if A equals B, it would be plus log of 1. The log of 1 equals 0, so the big deal here is pH equals pKa. Right? Right. So that's significant. pH equals pKa. It's also the best buffer region because you're going to have substantial amounts of both base and acid. It's going to have the greatest buffer capacity because you have lots of it relative to each other. Remember, we're talking about this. So if you have lots of it, it's going to be tougher to overwhelm the buffer. You can't overwhelm buffers. They don't buffer forever. So let's look at some more problems. Number 1. Consider a solution of hydrocyanic and sodium cyanide, which the following statements is true. Okay, so the molarities aren't the same, but it is a buffer system because I have a weak acid and its conjugate. The solution is not a buffer because HCN is not equal to CN negative. That is false. They don't have to be equal. They just have to be present in some amount. The pH will be below 7, so it's going to be acidic because the concentration of acid is greater than that of the base. That seems to make sense. OH negative is greater than H positive. That's kind of the opposite, so these guys kind of are opposites of each other. The buffer will be more resistant to pH change from adding strong acids. If I'm adding strong acid, it will be a better buffer. Well, looking here, I have more acid, and I have less base. So if I add strong acid, it would not be better at absorbing that. All of the above are false. I know this has to be false because I know B or C would be right. Now, originally you think, oh, concentration is going to dictate what's the better acid and what's the better base. But it's not. Remember, strength is usually a factor of 1,000 times difference or whatever it is. So we want to look and see Ka for HCN. That's a pretty weak acid. 10 to the negative 10th, that's not very impressive. What would the Kb be for Cn negative? So, and remember, Kb times Ka equals 1e negative 14. Now, if your Kb, or your Ka, is e to the negative 10 equals e to the negative 14, then your Kb is going to be e to the negative 4-ish, which means it's a better base than your acid is an acid. So that means that cyanide is going to be 1,000,000 times better base than HCN is an acid. So if it's a better base, you're going to have more hydroxides. For a solution equimolar in HCN and NaCN negative, equimolar, so they have equal amounts, so acid equals base, if I'm thinking Henderson-Hasselbalch, so pH equals pKa, just run through all the things that should pop into your head. This is an example of the common ion effect. Yes, the common ion is CN, and when HCN dissociates, you get H positive and CN negative. The H positive is larger than it would be for the HCN if only HCN was in solution. I'm going to equilibrium that one first. And I'm doing it in the Arrhenius thing, which we hate to do, but I'm going to. The H positive is larger than it would be if only HCN. So if I add NaCN, I'm adding something on the right, so it would shift to the left, so the H positive would not be larger. That would be false. I'm just going to go through the rest of the choices. So B is got the answer. H positive is equal to Ka. Remember we said pH equals pKa? So how do I get rid of the P's? You would, to get H positive, 10 to the negative pH or whatever it is, and 10 to the negative Ka. So those would be the same. If you add more NaCN, it will shift the acid dissociation equilibrium to the left. Yep, we just talked about that. I forgot when we were talking about that. Oh, for B, we were talking about shifting the equilibrium. If you add OH negative, so if I add OH negative, what would that react with? OH negative would increase the CN negative and decrease the HCN negative. So would OH negative react with HCN? Absolutely. So that would decrease HCN and increase CN negative. That's a true statement. Disturbing a buffer system. These are usually called titrations. A lot of times it's a titration. And what we're going to do is we're going to do ice in moles, not molarity. And it's really because the next thing that we learn about these buffer things, you need it in moles for equivalence points. Acid plus base goes to completion. That's very important. That's not equilibrium. That means you use stoic and limiting reactants, not minus X. Use Henderson-Hasselbalch equation for the pH using molarity or moles because the ratio is the same. The following question refers to the following system. 1 liter solution contains blah and blah. If one adds 0.3 liters of 2.02 molar KOH solution, what will be the change in pH? Okay, so what will be the change in pH? So I'm adding 0.02 molars. So I'm not adding a lot, and it's a buffer system, so the change should be very small. So I can tell you already if it's a buffer system, it's not B. So let's go ahead and figure out the pH of the starting one. pH equals pKa plus log base over acid. So this would be negative log 4E negative 4 plus log. My base would be NaF, 0.76, over my acid, 0.25. So calculators assemble. Negative log 4, E negative 4, enter, plus log, I already did quantity for me, 0.76 divided by 0.25, and quantity, and I get 3.88, that's not right. 0.76 divided by 0.25 equals 3.04. The log of 3.04, the log of 3.04 is 0.48 plus negative log 4E negative 4 is 3.88. Is that what I said before? I hope not. Anyway, my pH here would be 3.88. Now, what would happen if I add this other stuff to it? So I've got, if I'm adding OH negative, I'm titrating it, right? So the OH negative is going to want to react with the HF. So my reaction is going to be HF, let me change colors here since we're doing something different, plus OH negative would give me H2O plus F negative. Starting in a 1 liter solution, so I'm going to do all this stuff in moles. So my HF is 0.25. My F negative is 0.76. And then my moles for this would be 0.3 times 0.02, which would be 0.006. Now, since this reaction goes to completion, I'm going to do minus 0.006 minus 0.006 plus 0.006. So I'm going to have 0.2440, 0.766. Okay. So then I'm going to do my pH, same thing I did before. So pH equals negative log 4E negative 4 plus log base 0.766 over acid 0.244. Calculators assemble. Negative log 4E negative 4 was 3.397 plus log 0.766 divided by 0.244, 3.89. So what happens would be the pH, this was the second one, and I added a base, so the pH should have went up 0.01, but I'm betting that I did my math wrong on the first one a little bit, because I had 3.88. So these are so small. Notice how the pH change is very small. So if I got up 0.01, I'm betting at a rounding error somewhere. That would mean it was really down 0.01. So there you go. All right, next one. Solution contains 0.25 molar acid, 0.45 molar base. What is the pH of 0.16 molar is added? Okay, so I'm adding acid, so I'm going to react my base, A negative, plus my acid, H positive, yields HA. I'm going to do this in moles, make sure this is simple. It's 1 liter, so that's nice. So my A negative would be 0.45, and it tells me 0.16 moles is added. And then HA would be 0.25. So again, this would go to completion, so the smaller number is going to dominate here. So 0.45 minus 0.16 minus 0.16 plus 0.16. This is 0. This is 9, 29.29. This is 41.41. What's the pH of the system? pH equals negative log, well, 1E negative 6. Negative log 1E negative 6 is 6, so I'm going to make that easier. Plus log base 0.29 over acid 0.41. That's a 9. So 0.29 divided by 0.41, enter. Then I want to do log that answer. Plus 6 would be 5.84. 5.85, I guess that's right. This one's a little monster. What we have to do is you have solutions of blah, 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 and a pH of 3 is needed. So we're trying to do pH equals pKa plus log base over acid, but we're trying to solve for what this base over acid is, solve for ratio of base over acid. So I'm just going to call that X. And I'm going to take a couple of shortcuts here. 3 equals, I'm going to do the negative log of this on my calculator. Negative log 4E negative 4 is 3.40 plus log of X. I'm rearranging this, so subtract 3.40 from both sides, and I get negative 0.40 equals log X. And then anti-log both sides, so X equals 10 to the negative 0.4. Anti-log, negative 0.4, and I get 0.398. 1. Okay, so what that means is 0.3981 is my ratio of B over A. So that means B over A equals 0.3981. And it also means, if these things are being additive, looking at these guys right here, B plus A equals 1,000. So I could substitute in here where B equals 1,000 minus A, and then I could do 1,000 minus A over A equals 0.3981. Solving for A, which is my acid, and since and what happens there is solving for that, I get 714, which is our happy little spot right there. What species are present during titration? So don't write this stuff down. Those of you who did. When I start as titration, I have a, let's just say an acid. Oh, I can't erase that. I have an acid HA plus OH negative. So when I start out, when I add OH negative, it reacts immediately with HA to make H2O plus A negative. So in the very beginning, before I add any base, I would have just HA and water. As I add some, I'll still have HA left over, so this is the very beginning. Started the process, HA, all the hydroxide would be used up, so I'm still going to have H2O, and now I'm going to have more and more A negative, making a buffer, enemies. As I reach the equivalence point, I will have H2O, step 3, and A negative, and I'm going to put a star there, because we'll talk about that later, and we'll pretend that's all that happens. As I overwhelm the equivalence point, because I'm adding hydroxide, I'm going to have hydroxide, H2O, of course. The A negative will still be there. There will be no HA. So all that extra A negative will be there. That's it. My computer's been funny, so I'm just going to flash up the review thing and then let it boogie. All right, so have a good one and enjoy the weekend.